Hello and welcome to this review of oxidation numbers and redox reactions. Before we go, please make sure you've got your independent study and notes completed and in front of you while the clip is playing. There's a few basic definitions that go with this topic. Hopefully you've got them on a flashcard or in your notes, but I'll leave them up there for a little while, at least for some of the clip, until we run out of space and we need to get rid of them to make some room. So I'll go through each in turn. I've put them in a certain order for a reason. We'll start with oxidation number and how we actually arrive at oxidation number. So let's go through the oxidation number rules one at a time, and for each one I'll give you an example. So I'm not going to list them out and have them on the screen for you to copy out. That needs to be in your notes as indicated at the start of the clip. What I want to focus on is giving you an example or a meaning or context for each one. So if we look at the definition of oxidation number at the top of the page, it refers to atoms of another element. So even though in this chlorine molecule each chlorine atom has one of its own electrons involved in the bond, this doesn't count because the other chlorine is the same element, it's not a different element. So it has to be bonded to a different element. The second rule is that all the oxidation numbers in a neutral compound must add up to 0. So for example, all the combined oxidation numbers of one oxygen and two hydrogens must add up to 0 in water because water is a neutral molecule. So moving on to the next rule, all the oxidation numbers in a polyatomic ion must add up to its overall charge. So in the case of H3O+, everything has to add up to +1. And in the case of NO3-, they all have to add up to -1. So the next assignment rule concerns hydrogen, which is assigned an oxidation number of +1, except in the form of a hydride ion when it's -1. So what happens is because hydrogen is less electronegative than most of the other elements it combines with, it gets a positive oxidation number. So it involves one electron in bonding, so that's where the number is 1. And it's less electronegative than the other elements, so in these cases it's less electronegative than chlorine, and it's less electronegative than oxygen, so the hydrogen gets the positive oxidation number. But a hydride ion, on the other hand, is a special case where a hydrogen atom has gained another electron. It's unusual, but it does happen, and we actually go into the hydride ion a little bit more in the second year of available chemistry. But back to the point, what this does is it makes the hydride ion negatively charged, so this time it gets a negative oxidation number, but the number, as in 1, still represents the number of electrons it involves in bonding. Next up, we look at singular ions, such as those that have one atom only. So these have an oxidation number that is equal to their charge. And a quick reminder here not to call oxidation number and charge the same thing, because they're not. They're based on two slightly separate aspects of a species. So the next rule concerns oxygen. It always gets an oxidation number of -2, except when it's part of a peroxide. So the next rule is oxygen always gets an oxidation number of -2, except when it's part of a peroxide. So if we look on the left of the screen, you can see that water has 2 oxygen electrons involved in bonding with hydrogen. Now oxygen is the more electronegative out of those two elements, so therefore it gets the negative oxidation number, so it's -2, not +2. However, looking at H2O2, I've colour-coded the two different oxygen atoms. One has black circles, the other has blue circles to represent its 6 electrons. Now if you look at it closely, you'll see that each hydrogen atom only has 1 electron to share anyway. So what this means is the oxygen atoms are forced to involve only 1 electron each in bonding to atoms of another element, so the other element will be hydrogen. So therefore in peroxides, oxygen adopts an oxidation number of -1. There is one more exception to oxygen. This is the only other exception, and that's when it's combined with fluorine, for example F2O. So fluorine uses 1 electron to bond, and is the more electronegative element, in this case out of the 2, so it's assigned -1. Oxygen, on the other hand, has to use 2 electrons to bond to 2 fluorine atoms. And so as the less electronegative element, it's assigned an oxidation number +2 in this case. So the final rule is the group 1 and 2 and 3 metals. They'll always have the oxidation number the same as their group number, because their group number is the same as the number of electrons that they lose from their outer shell when they react in all circumstances. Therefore, that dictates its positive oxidation number. So therefore, group 1 will be +1, group 2 will be +2, and as you'd expect, group 3 would be +3. Okay, so now we've covered the oxidation number rules, we have to have a quick look at what a redox reaction might look like. So to do this, we need to introduce a couple more terms, a reducing agent and an oxidizing agent. Again, these should be on flashcards or in your notes, so you need to have those in front of you as we go through this bit of the clip. So what I'm going to do is put on a couple of examples of redox reactions and talk you through how to actually work out what's oxidized and what's reduced, because you'll need to be able to do this in exams. So if you're presented with a redox reaction and you're told to determine or prove using oxidation numbers what has been oxidized and what has been reduced, that's possibly the most common wording you'll find in exams. So the way to go about it is to assign the oxidation numbers. So we can start by assigning the number 0 to both the elements that are uncombined. So that's quite straightforward. And what you do here is you go for the things that you know can directly be assigned using the rules. So you've got oxygen or you've got hydrogen. Excuse me. Now the hydrogen uncombined is obviously an uncombined element, but hydrogen in a compound is +1. And oxygen in a compound is -2. And magnesium in a compound will adopt a +2 oxidation state because it's in group 2. Now H2SO4 has no charge overall, so all the oxidation numbers have to add up to 0. So what you do is you multiply each oxidation number by the number of atoms that have that oxidation number. So for hydrogen we've got 2 atoms each with oxidation number +1. So that gives us a total of +2. That doesn't mean the oxidation number has now become +2. It means the oxidation number is still +1, but it's applied to 2 atoms. With the oxygen, there's 4 atoms each with oxidation number -2. So 4 times -2 is -8. So that must mean to make the whole thing 0, the sulfur has to be +6. So applying the same idea to MgSO4 shows sulfur staying as +6. So now what we've got to do is identify what's been oxidized and what's been reduced. And we do this by looking at what oxidation numbers have changed. So we've got each and every element assigned an oxidation number now, so we have to actually look at the changes. Now an easy way to do this is to just draw arrows from one to the other. And you can label each arrow as an oxidation or as a reduction. So an oxidation has occurred for magnesium because the oxidation number has increased from 0 to +2. And for hydrogen, it's a reduction because the oxidation number has gone down from +1 to 0. So how would we word this so that we've answered the question? So if I scrub out the irrelevant oxidation numbers that haven't changed and leave the ones that have, we can say that magnesium has been oxidized from 0 in Mg metal to +2 in MgSO4. And we can say that hydrogen has been reduced from +1 in H2SO4 to 0 in hydrogen gas. So in terms of the oxidizing and reducing agents, magnesium is the reducing agent because it has been oxidized itself and hydrogen is reduced, and hydrogen is the oxidizing agent because it itself has been reduced and magnesium has been oxidized. So let's have a final look at something called disproportionation. So pause the clip and see if you can work this one out. Which element is disproportionated? I've highlighted the definition of disproportionation for you. So come back when you think you've got it. So I've assigned the oxidation numbers and all the easy ones. There's one missing. Let's see if you can spot it. It's the chlorine within HClO. So don't forget HClO is not a charged species, so therefore the oxidation numbers have to add up to 0. The only way this could work is if that particular chlorine is +1. Now, having a look at it, you can see that there's 2 chlorine atoms that are at oxidation state 0. So you can see that chlorine is simultaneously oxidized and reduced. So this means that chlorine has disproportionated. And this happens fairly often to halogens because of the fact that they're diatomic. So you'll come across it from time to time in A-level chemistry. It tends to happen to diatomic elements because one atom can be oxidized and the other one reduced. So that takes us to the end of this quick review. Thanks for your time. Hopefully it's been fairly useful to get you started on oxidation reduction, perhaps as a bit of a review of year 1 if you're in your second year. But until next time, thanks a lot and see you soon.